Extreme physics.
All right, let's take a look at waves. A wave is defined as a disturbance caused by the vibration of particles. Well, yeah, and I mean, sometimes you don't even really have particles. Like with light, maybe you do, maybe you don't, depends on how you look at the light. But most often, a wave is a disturbance caused by the vibration of particles. And it's a good way to transfer energy over a distance with a wave. And that's an important idea. Waves transfer energy without transferring matter. Ocean waves, they're always coming toward the shore. If you ever gone to the beach, the waves are coming in, but the water is not really coming in. I mean, the waves are. I mean, if every time the wave came in, it was just bringing water. Water's not piling up on the shore. The waves just keep coming in. So energy from the sun comes in, and there's no matter being transferred when we get the energy from the sun. And in fact, most of the energy on Earth comes to us through waves without the transference of matter. And then, of course, a stadium wave. Everybody knows a stadium wave. If you've ever been in a stadium, everybody gets, and it kind of goes around, right? Well, the people aren't going around the stadium. If you wanted to get a hot dog on the other side of the stadium, you couldn't take the wave over there. The wave's just people standing up and down, right? The wave is being transferred around the stadium, but the people aren't. So waves transfer energy without transferring matter. That's an important idea. Mechanical waves. Mechanical waves are waves that require a medium. An example of that is water waves, waves on water. Without water, you didn't have the wave, right? The water is the medium. So a mechanical wave is a wave that travels in some matter, and the matter itself is required for the wave. Sound is another example. You can't have sound without a medium. The medium we're used to dealing with sound in is air, but the reality is that sound travels even better in solids. It'll travel through metal or wood or anything like that. Quite efficiently, actually, and it also travels quite nicely through water. Travels better through water than air, and like a wave traveling through along a spring or a rope or something like that, which I'm going to show some examples of. I'm going to use springs for examples to show you the different types of waves in a moment. We're going to have to deal with a bunch of vocabulary in this unit, probably more so than in some of our other units. Waves propagate. It's just, when we say waves propagate, we just talk about them traveling. Like people walk, snakes slither, horses gallop, and waves propagate. So you're going to see that term used. We're going to be looking at pulses, which is a single disturbance, and that's called a pulse, and a periodic wave, which is the more common what we think of when we think of waves, and that is periodic means that the wave just keeps repeating, right? Boom, keeps going and going and going like that. All right. Now the waves you've seen here have been transverse waves. Those are waves where the vibration of the wave is at right angles to the propagation. In this case, the wave is traveling to the right, but the vibration of the particles are up and down. And here's a video to show you how that works. I'm going to send some waves down this spring. I'm going to send two types down. One is like this. And what's happening in this case is I have a wave that's traveling back, and it's hitting that barrier, then coming back and reflecting backwards. And the velocity of the wave is this way and that way, but the vibrations are this way. So you can see that the little coils move back and forth this way, but the wave travels that way. This is called a transverse wave. Right? And this is also considered a pulse, since I'm only sending one disturbance down and it's coming back, that is called a pulse. Boom. All right? That's a pulse. I could also send down a periodic wave, and a periodic wave is one that just keeps repeating itself. And so I go like this. But what you can see very quickly when I send a periodic wave down, that very rapidly it doesn't look like the wave is actually traveling either this way or that way. It looks like it's kind of standing still. This is called a standing wave. And what you're actually seeing is two waves. You're seeing the wave that's coming in and the wave that's going out laid on top of each other, and that's what's giving you the standing wave. If you watch very closely, you can see when I first start vibrating, you'll see the periodic wave going this way, but as soon as the reflected wave comes off, which is very soon afterwards, they start combining to give the standing wave. So see if you can see initially the if I do it as a kind of a periodic pulse, you can see that it is indeed traveling that way initially, and then afterwards it's still traveling that way, but because superimposed on it is the reflected wave, it looks like it's just, let me get the frequency right, it looks like it's just standing still. Right? It doesn't look like it's traveling either towards me or away from me. All right? So this is a transverse wave, a transverse pulse, a transverse periodic wave, and in this case, it's a transverse periodic wave that is setting up a standing wave. All right. So I will never actually be able to show you a periodic wave that is just constantly moving out, because I'm always in a finite space and there's always going to be a reflection back. I can do it with animation. I'll show you that with animation. But I can't physically do it like this because you're seeing an important property of a wave when it hits that pole. And one property of waves is when they hit a boundary, when they hit a change in medium, some of the wave will be transferred into the medium and some will be reflected. In this case, that pole vibrates a bit, so some of the energy goes into the pole and then some of it reflects. In fact, a lot of it reflects, if you can see that pulse going down. And you'll notice also the pulse, when it comes back on the other side. And we'll talk about that a little later. All right? So that is a transverse wave. So another common type of wave is what's called the longitudinal wave. And sound behaves this way. And that's where the vibration is parallel to the direction of propagation. When a wave travels, we say it propagates. So let's see if you can see this. This is harder to see. Well, you can see the pulse going back and forth. It's harder to tell how the vibration is, but the vibration is actually back and forth like this. All right. So this is, and that's too much. All right, I guess that's the end of the demonstration. And then we also have longitudinal waves. These are harder to draw and harder to represent in 2 dimensions. But basically the vibration is parallel to the direction of propagation. So when we draw them, we usually draw them like here the particles or whatever's vibrating is bunched up, and here they're spread out and bunched up. These are called compressions, and these are rarefactions where they're spread out more. And this compression zone travels down the wave, as does the rarefaction zone, and that's actually what makes the wave. Sound is a common example of a longitudinal wave. That's the way sound is when you talk. There's nothing coming out of your mouth. It's not going like this. It's going boom, 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 boom. It's vibrating out like that, and in fact, it's vibrating out in 3 dimensions spherically outside the vibration source. All right, so we got to learn some vocab. we got the crest. If we have a transverse wave like this, the crest are these high points as we've drawn them. That's a crest of a wave, and the trough is the low point, right there. And we can see the horse eating out of the trough, right? These low points is called a trough. We're going to talk about phase, and in phase are points on a periodic wave that have the same displacement from their equilibrium position and moving at the same direction. So they're in phase if they're in the same position and moving in the same direction. So it's basically when you have a wave like this, there are different points along the wave that are acting identically. And when like A and B are in phase, if this wave was moving to the right, I can't tell which way it's moving from the drawing, but let's say it was moving to the right, both A and B, they're in the same position and they're headed downward, right? A moment later, as this wave goes like this, A is going to be at that amplitude and B is going to be at that amplitude. So these two, A and B, we say are in phase with each other, and that's going to be an important idea. Here's an example, and then we have this thing called wavelength, and it's represented by the symbol lambda right there. Lambda, that's a Greek symbol, and it's the shortest distance between two identical points in a wave, separated by 2 pi radians or 360 degrees, because this is a sinusoid. If you look at this as a sinusoid, so this is a wavelength right here. It's the shortest distance between 2 points in a wave where the wave repeats itself, right? So here, the distance between these two crests is a wavelength. The distance between A and B is a wavelength. The distance between this trough and this trough is a wavelength. So the distance between any 2 points in a wave where the wave repeats itself. So like here, if I started here, I'd go, not a wavelength yet, right? It's at the same height as that one, but where this one was kind of going up, this one's going down. We're not, boom, 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 right there, right? That's a wavelength right there. Between here and here is a wavelength. And all right, now it's kind of a weird name when you think of wavelength, because with a periodic wave, we imagine it goes forever. So the wave itself has no length, but the repetition of the oscillation is what is called the wavelength. All right, so here we go. We got a wave like this, with like a rope or something like that, and we got this pulse like this, and it's headed to the right. And here's a knot or something that's on the hunk of rope or whatever that is. Why don't you take a moment and figure out what is going to be the motion of A as this pulse passes through, right? What's going to be the motion of A? Which way is it going to move, right, as this pulse passes through? Why don't you take a moment to figure that out?
Pause the video now.
All right, so what's this going to do when it goes by? Well, a moment later, everything's going to be moved to the right, right? And what's it going to do? This thing's going to move down, right? It's going to follow this down, and then it's going to go up, and it's going to go down, and it's going to stay there. Now, it's not going to move from this position. It's going to do all that here, right? It's going to go, well, when this thing passes by, it's going to go down, up, and down, right? This point A does not move right to left. It just moves up and down, right? This is a transverse wave. Let me show you another example of that with an animation. let's try this. So we got, yes, just a phase. Okay, so which pair of points are in phase? Why don't you list, so we got all these points, we got A, B, C, D, E, F, G, H. Why don't you list the pairs that are in phase and the pairs that are 180 degrees out of phase? What does it mean 180 degrees? Well, and what's this angle have to do with the wave? Well, I'm glad you asked. Here I have a little animation reminding us how the sine function relates to angles and all that good stuff. So here we go. We got the, remember from math class, we got the sine of an angle is defined as the ratio of the opposite side to the hypotenuse. And down here, I have a triangle. The red line is the hypotenuse, and the blue line is the opposite side. Now, and this is the angle right here. Right now, we're at 0 degrees. So you don't see an opposite side because it's a completely squished triangle. So the opposite side is 0, and the hypotenuse is 1. So 0 over 1 is 0. So our value is at 0. The sine of 0 degrees is 0. And then if we just bump that up a little bit, and we can see our triangle, we got a little bit of an angle, maybe 10 degrees or something like that. And we could see the opposite sides getting bigger. So this got a little bigger at this angle, whatever degrees it is, maybe 10 degrees, I don't know. And then as the angle gets bigger, the opposite side, it gets bigger. Hypotenuse is still 1, so the value of the sine function is just what the opposite side is if this is a unit circle. And then it keeps getting bigger, and this keeps getting bigger. The opposite over the hypotenuse keeps getting bigger. And the rate at which it gets bigger relative to the hypotenuse gets smaller as we go. It had its biggest jump right in the beginning because it went from 0 to non-zero values, so it had a big jump. And now it's kind of slowing down. And then when we get to 90 degrees, it equals 1 because the opposite side and the hypotenuse are the same size, right? And then as we go beyond 90 degrees, here we see the opposite side is getting smaller. Therefore, this is getting smaller. Boom, 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 boom. And when we get all the way to 180, our opposite side is going to be 0. Boom! And that's 0. And then we're into negative territory now. And we keep going around, getting bigger, 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 and -1. And then back to 0, which is the same as 360 degrees, like that. So, and that just keeps going around. So when we talk about the angle, that's what we're talking about, right? So when we say something is 180 degrees out of phase, that's what they're talking about. You're halfway through the sine cycle at 180 degrees. All right, so why don't you try and figure that out? Which pairs of points are in phase and which pairs of points are 180 degrees out of phase?
Pause the video now.
All right. In phase, it looks like, assuming this thing keeps repeating itself, it looks like A is at position 0, and what direction is it headed right now? It's going down, right? So I need another place that's there and going down. This D is in the same position as A, but it's going up. It's headed up. F is headed down. So A and F are in phase. Let's see, what else we have? We have B is anything. Oh, yeah. B is at this height, and it is headed downward if the wave is traveling to the right. Well, this right. That's confusing because my right's different than your right. But anyways, going this way, let's assume the wave's going this way. So then B is headed downward, and so is G. B and G are at the same height, and they're both headed downward. And C will be headed downward very soon, too, and so will H. C and H are in phase, and that's all the points that are in phase. All right, 180 degrees out of phase. A and D, right? They're in the same position, but A is headed downward and D is headed upward. A and D are 180 degrees out of phase. C and E are 180 degrees out of phase. And so is, let's see, C and E are, it looks like D and F are 180 degrees out of phase. And it looks like E and H are 180 degrees out of phase. All right. Phase is going to be real important. It gets used a lot in technology. All those fancy disks that don't get used anymore used phase to store information. CDs and Blu-rays and DVDs, those all used phase, the idea of phase to store data on those disks, right? Don't get used much anymore, but anyway, it's still phase still gets used a lot in technology. Frequency and period. These are important ideas. You may know these from math class. So let's take a look. A cycle is one complete repetition of a periodic wave. You got to know what that means. A cycle is just one complete repetition of a periodic wave. We say that's one cycle. Frequency is given lowercase f. It's a number of complete cycles completed in 1 second, and that's in units of hertz, either cycles per second or hertz. And we have and then we also have period. Period is a measurement of time, not surprising, capital T, and it's the time to complete one complete cycle, and that's in units of seconds, right? So frequency and period. So it's two different ways of describing the same phenomenon. For instance, if you're going to the dentist, right? So you should go to the dentist. They recommend you go to the dentist every 6 months or 2 times a year. One of those is a period and one of those is a frequency. They're both describing the same sort of thing, how often to go to the dentist, but in different ways. 2 times per year is the frequency at which I go to the dentist. It's the number of completions per unit of time, 2 times per year. 6 months is the period between going to the dentist. So I go to the dentist every 6 months. 6 months for every visit. So that's a measurement of time. So they're reciprocals of each other. The period is 1 over frequency, and the frequency is 1 over the period, right? So those are important distinctions. It's easy to confuse those, by the way. And if you just are strict with your units, you won't, right? You won't mess up if you stick with the units. If you ignore the units, well, you're going to run into problems. So units are your friend. If it has units of time, it's period. And if it has units of 1 over time, it's going to be frequency. All right. So here we go. We got an example. I want you to give this a try. What is the wavelength? Between A and B, we said that that's 6 meters between A and B. And so what's the wavelength here, right? We have multiple wavelengths here. You need to figure out how many wavelengths we have, and the whole thing is 6 meters. And why don't you try and figure out what is the wavelength?
Pause the video now.
All right, well, let's take a look at the wavelength. Let's see, we go here. We've got, boom, that's 1 wavelength. Boom, that's 2 wavelengths. Boom, that's 3 wavelengths. All right, so we have 3 wavelengths. So therefore, each of these wavelengths is one wavelength is 2 meters, right? 2, 4, 6, right? So 2 meters is the wavelength, not 6. 6 meters is the distance between A and B, right? The wavelength is the length for 1 cycle, and here's 1 cycle right here. That is 2 meters. If it takes 7 seconds for a crest to travel from A to B, what is the frequency? What is the period? right? So why don't you try that out? What you want to do is you want to write down, you got 7 seconds. That's one piece of information. And how many cycles are there in 7 seconds? Write down how many cycles there are. And then frequency will be cycles per second. And period will be seconds per cycle. So why don't you figure that out?
Pause the video now.
All right, so what's the frequency? What's the period? You know, whenever I have these, something like this, I always like to break this into its wavelengths. So here we go. We got from here to here's one wavelength. Boom. Another wavelength and another wavelength. All right. So, and then usually, you know, to figure out actually what the wavelength is, I would do this. I'd say 3 lambda, 3 wavelengths equals 6 meters. Therefore, 1 wavelength equals 6 meters divided by 3 equals 2 meters. I know this was easy enough to just look at and say, oh, that's 2. But this will help you even when the numbers get weird. So anyways, what's the frequency and what's the period? It takes 7 seconds to go from here to here, to go from A to B, right? So 7 seconds. So T equals 7 seconds to go from A to B is 7 seconds. That's not the period, of course. That is the time for 3 periods, actually. So we would have 3 cycles, right? This goes through 3 cycles. So we have 7 seconds per 3 cycles. And we also have 3 cycles in 7 seconds. Well, one of those is the period and one is the frequency. It's pretty easy to tell if you follow the units. Number 1. One of these is a unit of time. Can you guess which one? Yes, that's right. The one with the big T in it. That's the period. That's a measurement of time. Either of these a measurement of time? Well, this definitely isn't. This is per second. If it's a measurement of time, it's going to be in the measurement of seconds. This is the only one. This is 7 seconds per cycle. So this is the period. 7 seconds per 3 cycles, and the frequency is 3 cycles per 7 seconds. 2.33 seconds is the period. Now you could say seconds per cycle, right? That's fine. But a cycle is not technically a unit. And then we had 3/7.429 cycles per second. Or a cycle's not a unit. This could also be 0.429 per second, because a second is the only dimensional unit there, or 0.429 hertz, right? Hz, hertz, right? So probably hertz is probably the best unit for frequency. So we had and they're reciprocals of each other. The period is 2.33 seconds, and the frequency is 0.429 hertz. Amplitude. Amplitude. Both periodic waves and wave pulses share the wave characteristic amplitude. The amplitude of a wave is its maximum displacement from the rest or equilibrium position. All right. So this line that I have drawn here is the equilibrium position, and this thing, waves always oscillate about their equilibrium position. They oscillate about some point. And if there wasn't a disturbance, it would be this, whatever this was, it'd be laying along this. The amplitude is this height from the equilibrium position to the maximum excursion. That's called the amplitude. It's not from the lowest point to the highest point. That is not the amplitude. That's twice the amplitude. The amplitude is this, right? So with a periodic wave, make sure you're not measuring from here to here, right? That's not the amplitude. That's twice the amplitude. The amplitude, and it's clear with a pulse. You can see with a pulse why they define it from the equilibrium position. Because this doesn't have a negative excursion. This only has a positive one, right? Like this. So again, this is the amplitude from the equilibrium position to the maximum excursion from that point. So amplitude is the measurement of the energy of a wave. Large amplitude waves are loud, and large amplitude light waves are bright. So the amplitude is an indication of the energy in the wave, right? That's why they I don't know if you know the term amplifier, right? You got an audio amplifier or something like that. An amplifier makes things, it increases their amplitude. It makes the signal louder. That's what an amplifier does. It makes things not necessarily louder. An amplifier just makes the wave bigger, taller, more energy. It gives it a larger amplitude. The amplitude has no effect on the speed of a wave, right? If we got two waves traveling down a rope or something like that, they're going to be traveling at the same speed. The medium that they travel in is the thing that determines the speed of the wave. The amplitude doesn't matter. The frequency doesn't matter. And that's a good thing, right? If you're at a concert and you're far away and you got an instrument playing louder and another one playing softer, they're both going to arrive to you at the same time. Those sounds are, regardless of which one's louder. It really would sound like a mess if the louder things traveled faster and whatever, or higher frequencies travel faster than lower frequencies. If you were far away, by the time the music got to you, it'd be like, what is going on, right? But that's not the way it works. The only way to change the speed of a wave, a mechanical wave, is to change the medium. And since, like with sound, everything's traveling in the same medium through air, it's all traveling at the same speed, right? A loud sound travels no faster than a quiet sound, but a loud sound will travel farther because it has more energy. All right, so we're going to need to be able to calculate speeds of waves and stuff like that. And speed, of course, is just distance over time. And you always kind of want to derive this. Don't rely too much on your Regent's reference table. Speed equals distance over time. But what's the distance of a wave? Well, it's the wavelength is the distance. And the time to complete one wavelength is a period. So the speed equals wavelength divided by period. And since frequency is 1 over the period, speed can also be expressed as frequency times wavelength. Well, I know the speed of a wave. Frequency times wavelength. These are real important ideas when we study waves. And the medium affects the speed. The speed at which a wave travels is determined by the type of wave that it is and the medium it's traveling. Example, a sound wave travels 4 times faster in water than in air. We often think that it might not travel that great in water. And that's because if you've ever been in water and you hear people talking, like if you're in the pool and you're hanging out and you hear people talking, it sounds really muffled and all that. And that is not because sound doesn't travel well in water. It travels very well in water. It's just our ears aren't designed to couple with water. So we have a very inefficient coupling. When water gets on our ears, it just doesn't, it's not designed for that. So it sounds really muffled to us, but it actually travels quite efficiently. In fact, some of the loud noises we make in the ocean is supposed to, could really be causing whales and all these animals really a lot of stress because we're making the ocean very loud with our engines and stuff like that. Light travels 33% slower in water than air, right? So light travels very quickly through air. It travels best in a vacuum. And it does travel through water just fine, but slower. And you've noticed that there's something called refraction, which we'll study later, that because of the slowing down, light behaves differently. It bends. Sometimes it bends when it travels into water, depending on the angle. But anyway, so the medium affects the speed of a wave. And as you saw in the video, when a wave reaches a new medium, it reflects, right? Some of the energy will go into the new medium, and some of it will reflect. And that's going to be real important in a lot of ways. So here we have a pulse coming in. It hits the wall. The wall's a denser medium, and it reflects on the other side. We say that it reflected 180 degrees out of phase. It turns out that if it comes in and hits a less dense medium, it will reflect in phase. So when it reflects, it'll reflect on the same side. But anyways, we got reflection whenever a wave hits a boundary.
Extreme physics.